Welcome to geometry class. Today we're going to talk about the mid-segments of triangles. First of all, we need to define what a mid-segment is. It's pretty simple. Mid-segment of a triangle is a segment which connects the midpoints of two of its sides. So for example, suppose we have triangle ABC, and we have a midpoint here, we'll call that point M, and a midpoint over here, call that point N. I've identified point M and point N. Those are midpoints of two different sides. The mid-segment is the segment that connects those 2 points. Okay. Notice we talk about the properties of mid-segments, plural. Every triangle has 3 mid-segments. If we call this point O, and we say that point O is the midpoint of AC, you can see that we actually have one more segment, mid-segment here, and another mid-segment there. So every triangle has 3 mid-segments. Mid-segment theorem, let's take a look at that. It's a helpful rule, something that we'll be able to apply in a number of different circumstances. It says if a segment joins the midpoints of 2 sides of a triangle, then the segment is parallel to the third side and is half the length of the third side. Notice this hypothesis here. A segment joins the midpoints of 2 sides of a triangle. That's actually really just the definition of a mid-segment. So in other words, it says if you're dealing with a mid-segment, and the mid-segment is parallel to the third side and is half the length of the third side. Take a quick look at that. Here's a triangle. Suppose this is a mid-segment. Okay. The theorem says that this mid-segment is parallel to the third side and is exactly 1/2 its length. We will look at a proof of the mid-segment theorem, and then we'll look at the application. When we prove the mid-segment theorem, we're going to use a new type of proof. It's a kind or a form of proof we haven't looked at yet. It's called the coordinate proof. The coordinate proof is carried out in the coordinate plane using geometry and algebra. There's 2 main steps to the coordinate proof. Number 1, we begin the proof by placing the triangle, in this case, the shape we're trying to work with, in a convenient place in the coordinate plane. We'll use this triangle ABC, to do our proof. You may be tempted to think that there's something special about the shape of this triangle. We try to do exactly the opposite. There's nothing special about this triangle. It's just a generic triangle. Notice the first step says we begin by placing the triangle in a convenient place in the coordinate plane. There are an infinite number of places where we could set this triangle down in the coordinate plane, but we're looking for a convenient place. And it turns out one of the most convenient places is to take and park the triangle so that one of the vertices is right at the origin. So we'll just park that A right there at the origin. The next thing that will be helpful is to take and move one of the sides so that it's right on the x-axis, like that. So now I've taken generic triangle ABC and I've parked it in a place where it's a little more convenient for us to look at it. I've parked it so that one of the vertices is at the origin, and one of the sides is along the x-axis. The next thing we'll be able to do now, and it'll make it easier since we've taken those first step, we'll be able to assign variables to each of the coordinates of the vertices. There are a couple things worth noting here. First of all, I know the coordinates of point A. It's pretty straightforward. Point A has coordinates 0, 0. And I can see that because it's at the origin. I placed it there on purpose. That's why it was so convenient to place the triangle there, because when I parked it with vertex A at the origin, I gave vertex A some known values. Again, you may think that's something special about this triangle, but it's not. I can take any triangle in the world, park it in the coordinate plane, and slide it, rotate it, move it, so that one of the vertices happens to be at 0, 0. And so that'll always be a known value for me. Let's come over here and talk about point C real quick. Do we know any of the values for point C? The answer to that question is yes. No, the vertical value is 0 because it's on the x-axis. Up and down, of course. Do I know the horizontal value? The answer to that question is no. So I'll assign a variable to that. We'll call it A. And again, the vertical value is 0. Then let's assign some values to B. With respect to B, I don't have a clue where B is. It could be any place. So we'll say that B's horizontal position is, in fact, lowercase b, variable B. B's vertical position is at C. Now you can see we've assigned unique variables to all of the unknown values, A, B, and C. And now we're in a position to actually go ahead and prove the mid-segment theorem. The first thing I need to do is identify the midpoints of AB and BC, because that's really where we will want to work with our theorem. So I'll just construct those midpoints here in the software, and we are working with this midsegment right here, segment MN. The first thing we need to do in the proof, now that we've got it set up, is actually identify the coordinates of points M and N. So M, remember, is a midpoint, and so the midpoint formula looks basically like this. We know it's x1 plus x2 divided by 2, y1 plus y2 over 2. That's my midpoint. So in this particular instance, we end up at the point M. Coordinates of point M are 0 plus b over 2, 0 plus c over 2. That's my x and y value. And we can simplify those a little bit. 1/2 b and 1/2 c. Let's take a look at n now. N has these values, a plus b over 2, 0 plus c over 2, and that simplifies to 1/2 a plus b, 1/2 c. So this whole picture looks a little bit strange, but these are my coordinates of my midpoints based upon the values I assigned to my actual vertices in the triangle. So the first question we want to answer, the first part of the theorem, is this question as to the slope. How does the slope of the midsegment compare to the slope of the third side? Let's talk about the slope of the third side first. Remember, slope, lowercase m, is equal to delta y over delta x. And in this case, we can see that the third side of the triangle goes from the points, I'll just write these up here for a moment, goes from 0, 0 to A0. That's my third side. When we talk about delta y, you can see it's 0 minus 0 divided by a minus 0, which is 0 over a, which you can see, I think, equals 0. So the slope of my third side is 0. Let's go ahead then and take a quick look at the slope of the midsegment. You'll notice the midsegment, to talk about the slope of the midsegment, we really need to talk about the slope of segment MN, and we have the points here. And right now, all I want to really do is just look at the y values, 1/2 c, 1/2 c. You know that slope is equal to delta y in the numerator. And so when we talk about delta y here, that means 1/2 c minus 1/2 c. Let's just leave the denominator alone for a minute. You can see 1/2 c minus 1/2 c is equal to 0. And so my slope of my midsegment is also equal to 0. What does that mean? Well, we have the slope of the third side is 0, and the slope of the midpoint is 0. So therefore, we've already proven the first part of the theorem, that the midsegment is always parallel to the third side. Again, let's take a look at this triangle over here. Notice again that any way I want to change this triangle, for instance, if I've moved vertex B, wherever I want to move it, any triangle you can think of where we will find that all of this holds true. Notice how I cannot change the fact that MN is parallel to AC. No matter where I go, it's parallel. Even down here, it's parallel. So you can see the proof, the mathematics is backing up what we're observing happening in the diagram. Next question we need to answer is this question about length. Is MN 1/2 of AC? Let's take a look at that. Go back over here. To do that, I'm just erase some of this, get some of this out of here. Okay, we have the points MN, and remember we also have these points A, which is at 0, 0, and C, which is at A0. And so we can very easily find the lengths of these segments. We could use the distance formula, but remember, these segments are both horizontal, and so we can use a much simpler segment addition postulate. So when we talk about AC, the length of segment AC, notice that it's A minus 0, or simply A units. It's A units long. When we talk about MN, we do the same thing. Notice that, again, the Y values are the same, which means it's a horizontal segment. So all we need to do is take the difference of the X values. In this case, MN is equal to 1/2 A plus B, that's the X value of N, minus 1/2 B. And this, of course, is the X value of M. Let's see what we get. In order to solve this, we really need to distribute the 1/2 over the binomial here. So we end up with 1/2 A plus 1/2 B minus 1/2 B. And that is equal to, you can see what 1/2 B minus 1/2 B actually cancels. And so we have simply 1/2 A. That is the length of segment MN. So if we ask the question, did we prove the second part of the theorem? The answer is yes. Here we've proven that AC, segment AC, the length of segment AC, is equal to A units, and the length of segment MN is equal to 1/2 A units. So it is half the length. And again, if we go back to our diagram here, we move around some of these pieces just to get an idea. You can see, I think, that no matter what I do here, this segment MN is always half of segment AC, no matter what we do. And it doesn't really matter which point we move either. You can see that there as well. So, a little bit of perspective on that. Let's look at a couple problems and see what we can do with this. Here's a diagram, triangle EFG, and it says, stipulates here that H, J, and K are midpoints. So since those are midpoints, that means segment HJ is a midsegment, segment JK is a midsegment, and segment HK is the third midsegment. So we've got three midsegments. And the problem we want to know, the thing we want to find out here is we want to find the length of HJ and the length of JK and the length of FG. Okay, so we'll go ahead and start with HJ first. Here we can see that HJ is equal to 1/2 EG. HJ equals 1/2 the third side, which is EG. And we know that EG is 100. So HJ equals 1/2 times 100. Therefore, HJ is equal to 50 units. So that was pretty simple. HJ equals 50. Let's go ahead and look at JK now, see if we can find JK. JK is here. We know that JK is equal to 1/2 EF. JK equals 1/2 EF, because EF is the third side, parallel side there. And we can see that EF is equal to 60. So JK equals 1/2 of 60. And therefore JK equals 30 units. 30 units. Okay, last problem asks us to find FG. This problem's a little bit different. Here we're working from information about a midsegment that's given, that says 40. And we're trying to work out to the third side. So, what do we know about FG? We know that FG is equal to twice the value of HK. Now, let me just talk about that real quick. If you didn't like that, if you wonder, well, where'd that come from? To state it a little bit differently, HK is equal to 1/2 FG. So if we want to solve this for FG, we just multiply both sides by 2. And we end up with FG equals 2HK. All right, HK is known to be 40. Therefore, working from here, FG equals 2 times 40. And therefore, FG equals 80. So that's one of the ways we apply it. Straightforward application. Notice again that these sides, the corresponding sides, are all parallel. These are parallel. All right, here we have again triangle DEF, and it tells us that A, B, and C are midpoints. So we're looking at three midsegments here: AB, BC, and AC. And the problem asks, name pairs of parallel segments. Name pairs of parallel segments. So we just pick a place to start. Let's just start with AB. And we'll just say AB, segment AB, is parallel to segment DF, the third side. AB and DF. Then let's go ahead and move on to AC. So segment AC is parallel to segment EF. And then the third one, we have BC. Segment BC is parallel to segment ED. All right, let's look at one last example. Here in this example, we have a lake, and the idea is to build a bridge over the lake from point C to point D. And our question is, how long is that bridge? How long is the bridge? Or in the diagram, how long is segment CD? That's the question. How do we find it? First of all, we need to look around and figure out if there's any other information we know about the diagram. You can see we have this triangle in here. And we could ask the question, is point C a midpoint of one of the sides of the triangle? Since we know that there are two segments, 963 feet, that means these are congruent. And that, of course, means that point C is, in fact, the midpoint. Well, point D is a little more obvious. We have these congruent symbols here, and so we know that point D is also a midpoint. Therefore, since segment CD connects the midpoints of two sides of a triangle, segment CD must be a midsegment. Once we identify segment CD as a midsegment, we know that the midsegment theorem is in play. And what does the midsegment theorem say? Two things. Number one, that segment CD is parallel to the third side. This is the third side over here. And number two, that segment CD is 1/2 the length of the third side. Therefore, in this case, segment CD is 1,320 feet. And we now know the distance from C to D. And you can see that in real life, this may actually be helpful. And in fact, surveyors use methods like this all the time. It's really difficult to walk across and measure this segment through the water. So instead, there are times when they may survey around the lake and use their surveying measurements in order to determine the distance from C to D. We can do that with geometry. That is our study of midsegments in triangles and the theorems that pertain to midsegments. Make sure you do a couple practice problems, and as always, if you have any questions, send me an email.